Ben flips a coin 10 times and then records the absolute difference between the total number of heads and tails he's flipped. He then flips the coin one more time and records the absolute difference between the total number of heads and tails he's flipped. If the probability that the second number he records is greater than the first, can be expressed as A over B for positive integers A, B, with GCD of A and B equal to 1, find A plus B. Okay, so what can we notice here? Let's say, let's take an example. Let's say Ben flips 7 heads and 3 tails. Then the absolute difference between the number of heads and the tails he's flipped is 4. Okay, so now he flips the coin again. If he flips a head, he'll have 8 heads and 3 tails, which means the absolute difference would be 5. If he had flipped a tail, he would have flipped 7 heads and 4 tails for an average difference of 3. So you see that in one of the cases, his positive difference is, his absolute difference is greater than the previous one. And if in one of the cases, his absolute difference is less. If we try another example, let's say he has 2 heads and 8 tails. Well, the absolute difference between the number of heads and the number of tails is 6. Now, if he flips the coin the 11th time, he might get a 3 and an 8, or he might get a 2 and a 9. In one of these cases, the absolute difference is 5. In the other case, the absolute difference is 7. So you see that if the number of heads and the number of tails are not equal, then if he flips a head and the heads were greater than the tails, then the absolute difference would increase. Because if you had A heads and B tails, we've already used A and B. Let's say he has H heads and T tails, and H is greater than T. If he flips another H, his difference would be H plus 1 minus T. If he flipped another tail, he'd be H minus 1 minus T, right? So if the heads are not equal to the tails, the probability that he flips another one of the greater of the two quantities is 1/2, right? The probability that he flips another head is 1/2. Probability that he flips another tail is 1/2, and whichever one was greater, if it increases, then the absolute difference would be greater as well. However, what happens if you had 5 heads and 5 tails? The absolute difference is 0. And in this case, no matter if he flips a head or if he flips a tail, the absolute difference will be 1. Like if he flipped a head, he'd be at 6 and a 5, which has an average difference 1. If he flipped a tail, he'd be 5 and 6, and that also has an absolute difference 1. So in either case, you see that the absolute difference increases if he flips the same number of heads and tails in his first 10 flips. So what's the probability that he flips 5 heads and 5 tails? Well, the probability that happens is 10 choose 5 over the total number of outcomes, 2 to the 10. And the reason is because, let's say you flipped 5 heads and 5 tails. Then the order in which those heads could be flipped in is, it could be like H, T, H, H, T, H, T, 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 H. It could also be H, 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 T, 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 right? And essentially what you're doing is, for any order, you have 5 heads and 5 tails, and you're rearranging this. You're arranging this in some order. You're permuting it. And if the heads and the tails had all been distinct, then you'd have how many ways to rearrange them? 10 factorial, because there are 10 of them, if all of them are unique. But you can see that not all of them are unique, because all of the heads are identical to each other. All of the tails are identical to each other. So you see that if you have something like, let's assume that all of the heads are distinct and all of the tails are distinct, right? That's how we got the 10 factorial. If you rearrange this around and all the heads and tails are distinct, you get 10 factorial. But this, for example, this order is identical to H2, H1, and then the remainder of this stuff is all the same, right? Because H1 and H2, you really can't differentiate between them. Similarly, you can't differentiate between H1 and H3, so you could swap those around, and basically you could swap any of the H's around with each other, which means that for every one of these permutations, there are actually 5 factorial of them, because there are 5 factorial ways to arrange these heads. And each of those 5 factorial ways gives you an identical sequence. So you divide by 5 factorial and 5 factorial again for the tails, which is why this is equal to 10 choose 5. And of course, the number of total possible outcomes is 2 to the 10, because each flip can either be a head or a tail. And there are 10 flips, 2 possible outcomes for each flip, 2 to the 10. So this fraction is equal to 252 over 1024. And this is equal to, this is going to be equal to 63 over 256. So this is the probability you get 5 heads and 5 tails. And remember, what we wanted is this probability that we get 5 heads and 5 tails, times what's the probability that the absolute difference increases? We found that was 1. And what's the probability that you don't get 5 heads and 5 tails? That's just 1 minus this thing, which is 193 over 256. The probability that your absolute difference increases here is, we found, was 1/2. So you just take the sum of this, you get 63 over 156 plus 193 over 256. This is 126 over 512 plus 193 over 512. This is equal to 319 over 512. The sum of the numerator and the denominator, because those two numbers are relatively prime, their sum is 831, and we are done.